That's great, but what happens if the angular speed changes? Here's a wheel going down an incline. We've got the center of mass's linear velocity, v, is increasing. The angular velocity is increasing. Note the white dots represent the places where each spoke touches the incline. The dots are evenly spaced apart, so the wheel must rotate faster if the center of mass is moving faster. Here's a pulley with a string wrapped around it. The free end of the string is connected to a hanging mass. The hanging mass has a downward velocity that is increasing. The angular velocity of the wheel increases as it gets further along its journey. The brown pieces of the rope are set to where each spoke of the pulley touches the rope. The brown spots are evenly spaced apart, so the wheel must rotate faster if the block falls faster. When angular speed omega changes, we say that an object has angular acceleration. The symbol is lowercase Greek letter alpha, right there. Angular acceleration is the change in angular velocity over the change in time. No angular time, it's just time. The units are rads per second, which is just how many radians per second are gained every second. This is exactly like linear acceleration, which is the change in velocity over the change in time. Meters per second squared tells us how many meters per second of velocity are gained every second. We started with an equation that relates angular displacement theta to length around a circle. S equals theta times r. Dividing both sides by t, we get angular speed, v equals omega times r. If we divide both sides by time again, we're going to get v over t, speed over time, which is tangential acceleration, how much speed is gained or lost. We also will get omega over t, which is angular acceleration. So we end up with a equals alpha times r. Tangential acceleration equals alpha times r. Center of mass of the wheel has an acceleration a down the incline. The wheel's rotational motion is increasing, so it has angular acceleration alpha. The relationship between these two quantities is a equals alpha times r. And of course, r is the radius. The wheel's rotational motion is increasing, so it has angular acceleration alpha. The relationship between these two quantities is a equals alpha times r, where r is the radius of the wheel. Double pulley. So we have a larger pulley and we have a smaller pulley. The red wheel is connected directly to the green wheel. Both wheels rotate together, so they must always have the same angular speed omega. Because both omegas are increasing at the same rate, both wheels have the same angular acceleration. But the green block accelerates down faster than the red block accelerates up. Why? Green block is attached to a longer radius, so it has a higher acceleration. A equals alpha times r. So if alpha is the same, radius is bigger, that means acceleration must be bigger. Red block is attached to a shorter radius, so it has a lower acceleration. Again, alpha is the same, so we have a smaller radius, which leads to a smaller tangential acceleration, speed-changing acceleration. The object in the animation travels around its circle with a constant speed v. Therefore, it has a constant angular velocity. The relationship between these two is v equals omega times r, where r is the circle's radius. Note that the velocity vector is tangent to the path, and there is centripetal acceleration, which is that tiny red one, towards the center of the circle. Remember that centripetal acceleration equals v squared over r. If we combine that with v equals omega times r, we get another version of centripetal acceleration, which is omega squared times r. An equation worth remembering. It's given to you on the equation sheet, but at the same time, we don't use it often enough to have it specifically at the front of our brain, so putting in some effort to remember that one will serve you well. This object doesn't keep a linear speed or angular speed. for the lower right part of the circle, the object has slow constant velocity and a slow constant omega. The object gains speed as it goes around the lower left part of the circle, so we're speeding up right here. Now it has a fast constant velocity and a fast constant angular velocity around the upper left part of the circle. The object then slows down around the upper right part of the circle to return to its original velocity and angular velocity. As the object speeds up along the lower left part, there's a yellow tangential acceleration vector pointing in the same direction as velocity. If there's tangential acceleration in the same direction as velocity, what are you doing? Speeding up. Because there is tangential acceleration, there is angular acceleration, according to tangential acceleration equals alpha times r. Because both your velocity and angular velocity are increasing, the centripetal acceleration increases. So, looking at centripetal acceleration equals v squared over r. If the velocity is increasing, that means our centripetal acceleration is increasing. Over here, if our angular velocity is increasing, that means our centripetal acceleration is increasing. In this animation, linear velocity and angular velocity both double, so centripetal acceleration is multiplied by 4, because if you double v right here, we have to square that too. See how the gray rings show that the red centripetal acceleration vector becomes 4 times as long. As the object slows down in the upper right part, there's a yellow tangential acceleration pointed in the opposite direction because that's what needs to happen for you to slow down. Because there's tangential acceleration, that means there is angular acceleration. Tangential acceleration equals angular acceleration times a radius.